And finally, we have homoscedasticity, or its opposite, heteroscedasticity. So what we want is homoscedasticity. In other words, we have the same variance given any value of the explanatory variable. Heteroscedasticity is when that fails. We've got a different variance at different levels of the explanatory variable. So let me show you what that looks like. If we graphed our, definitely don't want to use that one. If we graphed our residuals, and let's say this is 0. Okay, so if we graphed our residuals, what we'd like to see is a similar level of variance as we go move along the x-axis. So what we don't want to see is some change in the variance. Okay, so maybe this is represented here where we're kind of fanning out. Okay, so this would be heteroscedasticity. Luckily for us, we can easily get around this in Stata by using the robust option. Okay, so we've got robust standard errors because basically what the only thing this has to do with what we're doing is it's going to increase, artificially decrease our standard errors. Okay, so we're going to use, if we use robust as our command, as our option for a regression command, then it is going to give us robust standard errors, and so this won't be a problem. And again, luckily for us, if we use robust standard errors, it won't hurt us if we have homoscedasticity, but can help us if we have heteroscedasticity. Okay, so there's usually not any reason to not use the robust option. Go ahead and use it. All right, so if we have SLR 1 through 4 satisfied, then we would say that beta 1 and beta 0 hats are unbiased estimators for beta 0 and beta 1. If all 5 are satisfied, then we actually have what's called the best linear unbiased estimators, or BLUE. Okay, so what makes something best is that the variance is as small as it can be for any model. Now, if we move over to multiple linear regression, these assumptions are going to be very similar to SLR, so I'm going to go through this pretty quickly, but there are some slight differences, and we'll go over them. The first one, linear parameters, that's going to be the same. We're going to have more coefficients here. However, the parameters are going to be very similar. They're going to be linear. So let's take a look at what that would look like. So y equals beta 0 plus beta 1, x1 plus beta 2, x2, and so on. So we'll get to up to beta k, xk. Okay, so these parameters, the coefficients, and that includes our intercept, those are all going to be still linear. Okay, so it doesn't matter that we have added multiple dimensions if we were to physically graph this. The point is that they are still linear. Random sampling, so there isn't really any change here. No perfect collinearity. So this is actually an extension of SLR3. It's very similar. So originally, if you recall SLR3, we were saying that x has to vary, and I showed you y. Now we have to say that not only x must vary, but also all linear combinations of all of our right-hand side variables, they must vary. Okay, so for example, and this is getting ahead of ourselves if you don't remember dummy variables, but let's say we had everyone in our data set identified as either female or male. Okay, and so let's say we've only got a couple of observations. And so the first observation, no, they didn't identify as female. The second one did. And let's say we had another variable called male, and the first observation they identified as a male, and thus, again, they couldn't have identified as a female at the same time in this data set. And so the second observation, well, that person said that they identified as female, so they could not have also identified as male in that same time. So if we took the linear combination, we just add these things together, we see that there's no variance there. Okay, so for a similar reason, we need to have variance here. So you'll see a lot of times for things like gender or anything else where something like this might happen, we omit one of them. Okay, so we just don't include that one, and that the one we omit becomes our base category. Okay, and we'll talk a little bit more about that later, but that's just something we need to keep in mind, that we're going to have to omit one of them in order to satisfy this no perfect collinearity. You'll notice this data will automatically drop variables that are collinear. Zero conditional mean. This is largely remains the same, except for now the error must be 0. Must be expected value of the error must be 0 given not just x1 but any of the other x values. Homoscedasticity. So this is the same. The error has the same variance given any value of any of the explanatory variables. And we've also added in a new one, normality. Now actually there is an SLR6, but as we were going through the course we hadn't gotten to as a point where we needed to talk about that one yet. And this one is normality. Okay, so if we remember, this is in reference to the error term, and we're saying that it's independent of all x terms. It's normally distributed with a 0 mean and variance sigma squared. So why is that important? Well, if that is the case, then the difference between we can say the difference between our estimate of beta j hat and beta j, we can say the difference between them divided by standard error of beta j is t distributed. Okay, so if you remember what t distribution is very similar to z distribution. In fact, it actually turns into the z distribution as our observations increase. Okay, and so why is this important? Well, if we know what our distribution is, we can perform some hypothesis testing and do some actual testing of the statistical significance of our coefficients. Right. So let's go through the 4 main steps of hypothesis testing. So the first step is we need to state our null and our alternative hypothesis. I say H1 here, and that is correct, but you could also have it as HA, which is what I have it down here as. So H1, HA just means the alternative hypothesis. H0 just means the null hypothesis. Right? So we need to first choose what sort of test we're going to do. Are we going to do a two-tailed test, a right-tailed test, and a left-tailed test? Which one are we going to do? Okay, so in other words, if we're doing a two-tailed test, our null hypothesis is that beta j is equal to 0. That's going to be the case in no matter which one we choose. But what differs is the alternative hypothesis. So for a two-tailed test, we say, well, simply beta j is not equal to 0. For a right-tailed test, we say beta j is greater than 0. And for a left-tailed test, we say beta j is less than 0. Next, we choose our alpha, which is our significance level. It's the probability of rejecting our null hypothesis when it's true. And we can use this to determine our t-critical values. All right, so if you check in the back of this this review, I have a t-table, so you don't have to go looking for very far for the t-table. But what you do need to do is you need to know your degrees of freedom, and you need to know whatever the significance level. If I'm asking you how to do this or to do this on the exam, I'm going to go ahead and give you the significance level that I would like you to perform this for. Okay, so you just take that significance level, whether or not you need to know whether or not you're going to do a two-tailed test or a one-tailed test. And you need to know your degrees of freedom, which is just the number of observations minus the number of independent variables minus 1 for our coefficient. Okay, so in other words, k minus 1 is the total number of statistics that we're simultaneously creating. So we subtract that number of statistics off from n, and that is going to be our degrees of freedom. All right. We find our t critical value using that, our t critical value, and we use that to find our rejection region. Okay, so our t critical value, oops, keep using that one. Our t critical value for a two-tailed test, we use both the positive and the negative of that value, and we find that the area under this curve is going to be equal to alpha over 2 on this side and alpha over 2 on this side. So this is going to be our t critical value. This is our negative t critical value. If we're doing a right tail test, all of the probability mass is on one side. And if we're doing the left tail test, it's on the other side. Okay, so here we're splitting, in the two tail test, we're splitting the probability mass into sides on either side. And we're doing it for the one tail test. For the right tail, where it's going to be on the right side, left tail is going to be on the left side. So that's going to be our second step, is to set this up. And I would suggest always drawing this out. Third step, reminder, we're going to use compute the t-statistic, and this is going to be using regression results. Okay, so we've got this beta j